In this lecture, we will take a closer look at how spectral editing could be achieved in NMR spectroscopy. Before we go there, I would like to revise a few concepts that would be helpful as we go on to the DEPT experiment. Let's take a simple 90-degree Y excitation followed by acquisition. For a single spin I, I'm sure you would remember during this acquisition period, your density matrix would be of the sort Ix cos omega it plus Iy sin omega it. And if you might recollect, taking the trace with respect to I plus resulted in the final form, which is going to be e power I omega t, which when Fourier transformed gives you a resonance at capital omega I. Let's take a two-spin system where you have Is. Then what ends up happening in such a case is that we first evolve with respect to chemical shift, in which case you're going to have the same thing as above, cos of omega it plus Iy sin omega it, followed by J coupling evolution. We are at liberty to do something like this, largely because the 2IzSz commutes with the chemical shift Hamiltonian. So this is going to be cos of omega it times Ix cos pi jt plus 2Iysz sin pi jt plus sin omega I times t Iy cos pi jt minus 2Ixsz sin pi jt. You would remember the terms here would therefore finally provide you trace of I plus to sigma. It will end up being exp I omega it times cos of pi jt. Cos pi jt ends up coming because there's a cos component to both of this. And if you might recollect, this would end up giving resonances at omega I plus minus pi j when you Fourier transform. So this was what we had learned. Let's continue further for the same pulse program. After having done this, how will something like an IS2 behave? We have just seen how I behaves. We have also seen how IS behaves. Now the question is, how will IS2 end up behaving? So in order to do that, all that I have to do is to continue from here and have another 2 pi j IZSZ evolution. So let us see what we end up getting there. Cos omega it times cos pi jt whole multiplied by Ix cos pi jt again plus 2Iysz sin pi jt. The next term, which is, let me put a plus sign here, plus cos omega it sin pi jt. The sin pi jt ends up coming from the factor that was present before, 2Iysz cos pi jt minus Ix sin pi jt. Then you have one more term, actually two more, sin omega it cos pi jt times Iy cos pi jt minus 2Ixsz sin pi jt plus sin omega it sin pi jt times, we should have a negative sign, no way, 2Ixsz cos pi jt plus Iy sin pi jt. So when you have these many terms, one has to be a little careful on how we deal with it. But overall, it suffices to say that we will only be focusing upon the Ix component and the Iy component. So let us write what is the Ix component works out to be. It is going to be cos omega it cos square pi jt minus cos omega it sin square pi jt. Then let's go for the Iy component plus Iy times sin omega it cos square pi jt minus sin omega it sin square pi jt. This might seem a little nebulous, but I'm sure we'll be able to understand it as we go forward. So now let's look at these terms so as to quickly interpret what's going on. So you have something like Ix cos omega it times cos square pi jt plus Iy sin omega it cos square pi jt. Taking the trace of this density matrix would end up giving you exp omega I t times cos square pi gt. And this can be rewritten as cos pi gt times cos pi jt. We are writing in such a way so that it helps you understand things better. If you might remember, this gave you resonance at omega plus minus pi j. So therefore you have another modulation. What it ends up doing is to give each one of them. So basically you have omega I plus pi j and omega I minus pi j, both of which further split with another pi j. So it's going to be omega I plus 2 pi j and omega I, and this one is also going to give you omega I and omega I minus 2 pi j. So therefore, since there are two signals that add up on top of each other, so you're going to get a resonance at omega I plus 2 pi j, 2 times the intensity at omega I, and then another at omega I minus 2 pi j. So therefore, when you take the difference between each one of them, you get the 2 pi j, which is a scalar coupling. And if you take the difference between the edge ones, you're going to get something like 4 pi j. So this helps you understand and illustrate how I versus IS and IS2 system would end up behaving, and we ended up evolving J coupling one more time. So similar would be the exercise that we would end up doing for the DEPT experiment, and compare and contrast it with the different types of CH, CH2 and CH3 modulations that we get, which helps us do spectral editing. Let me now begin with the DEPT experiment. The full form of it is called Distortion-Less Enhancement by Polarization Transfer. The main issue that we had seen with the refocused inept is that CH, CH2s and CH3s ended up showing phase distortions. The problem with phase distortions is that you may not be able to pick resonances that are very close to one another. So in order to alleviate it, the NMR community came up with a DEPT experiment. So it begins with a 90-degree pulse on the proton channel along the x-axis, a delay tau followed by a 180-degree pulse, and during this pulse, a simultaneous 90-degree pulse is applied in the carbon channel, followed by a tau delay. Then let's try the tau delay here. And then comes an alpha degree pulse along the y-axis on the proton channel with a simultaneous 180 in the carbon channel, followed by the tau delay, finishing off with acquisition on the carbon and decoupling on the proton channel. This is slightly different from the inert module, where in the inert module, in this portion, you had a 180-degree pulse on the carbon channel, followed by simultaneous 90-degree pulses. But of course, you had followed it by another tau 180 tau module in order to refocus your signal. Now, let us begin solving the product operator formalism for the DEPT experiment. So we'll start with a CH example where your initial density matrix is given by Hz. When you apply a pi by 2 pulse along the x-axis, you would end up getting minus Hy, followed by the tau duration where you have both chemical shift of I and scalar coupling of the IS spin, that is the CH spin. So rather than writing I, I'm going to write H and then Hc because we are thinking about a CH DEPT experiment. Before we go ahead and start writing everything in full glory, you are able to understand that this duration is a tau 180 tau duration during which the proton chemical shift will not evolve. On the other hand, unlike what we did with the inept where we applied it completely for the 2 tau duration, here we will apply one duration at a time. So let's continue. Since there will be no chemical shift evolution because you have a tau 180 tau module, you're going to end up getting minus Hy cos pi jt. Instead of writing that every time, I'm going to start writing that as Cj plus 2hx cz sj, where sj stands for sin pi j tau. If you set the tau equal to 1 over 2j, if you set the tau to 1 over 2j, you realize that cos 90 goes to 0, with sine 90 is the only term that survives. So I'm just going to propagate the second term that you see here. So therefore, let me only write 2hxcz followed by a 180-degree pulse along x-axis for the proton and then a 90-degree pulse along x for the carbon-13. Since you're applying the pulse along the x-axis, proton remains hx, there will be no change. On the other hand, the CZ, you're applying an x-phase pulse, therefore it's going to be minus CY. So now we'll apply it for the tau duration. Now be a little careful. You have many things. You have chemical shift of proton, chemical shift of carbon, and the J coupling between C and H. We just recollect the fact that proton chemical shift evolution won't happen in the tau region for the same reasons that we just saw a moment earlier. And if you once again pay close attention, you have a tau 180 tau module here, which will also therefore not result in carbon chemical shift evolution. You're only going to have J coupling evolution between carbon proton in this tau delay. Once again, you have only 2 pi j HZCZ that evolves. Nothing else evolves during this duration. But you can also recollect the fact that you have something like a multiple quantum coherence term, which we know for a fact will not evolve with scalar coupling. Once again, use the BCH formula and try to propagate it. You will realize that minus 2hxcy under the influence of scalar coupling will not evolve. So therefore, you're going to once again be wherever you were, which is minus 2hxcy. So now comes the next part where you have an alpha degree pulse applied along the y-axis for proton, and then you have a 180-degree pulse applied along x-axis for carbon-13. So let me rewrite the whole thing again. Minus 2hxcy applying an alpha degree y pulse on proton, 180 degrees x pulse on carbon-13. The carbon-13 is the easy part. It's all that it's going to do is going to change minus cy to plus cy. So I'm just going to erase this so that life is easy. All I have done is to operate the carbon pulse first and therefore get 2hxcy. Then since you're applying an alpha degree pulse, this is going to be 2hxcy cos of alpha. So you're applying a y phase pulse with x being the initial state. So it's going to go from x to minus z to minus hzcy sine of alpha. So for now, we have not decided what is alpha. So let's keep alpha the way it is. So far, we have come until this portion. Now, if you pay close attention, you realize that there are no more excitation pulses here, meaning that the order of coherence will not change from wherever it was. The order of coherence here is multiple quantum, which means that we are not going to observe it. On the other hand, this is single quantum. Of course, it's antiphase with respect to H, but let's not worry about it for now. And the chemical shift, therefore, of proton will also not evolve because you have 2hz term, which commutes with the chemical shift Hamiltonian on the proton. So all that we are going to do is once again evolve with 2 pi j HZCZ for a duration of tau. So what do we get here? Minus sine alpha 2hzcy cos pi gt minus 2hz times Cx will go with another 2hz Cx sine pi j tau. And if you may remember, 4 times hz square will be equal to 1. And therefore, this is going to get reduced to minus sine alpha 2hz Cy Cj minus Cx Sj. And if you set tau to 1 over 2j, like the way we did earlier, this goes to 0, this becomes maximum. Therefore, you're going to get Cx times sine alpha. So what we have done so far is to take the DEPT module and slowly apply the product operator formalism, carefully making sure we only evolve things that are required. We are able to realize that for a CH, the final density matrix is going to be given by Cx sine alpha. If this evolves with carbon chemical shift, of course, you're going to get exp I omega ct times sine alpha. Remember, alpha is the flip angle of the pulse, the last proton pulse that is present. If you repeat the similar exercise for the Ch2 system, keeping in mind that you have two protons that couple, remember the IS2 example that was solved, we carefully do it with all the other components that go, that multiple quantum coherence doesn't evolve with scalar coupling, you would finally end up with a density matrix, which is going to be Cx sine alpha cos alpha. You would be given a handout where each of the step would be carefully written out. And similarly, if you do it for the Ch3 spin system, you will end up with Cx cos square alpha sine alpha. So let me write sigma for Ch, which is Cx sine alpha. Now starts the interesting part of the spectral editing. You can array alpha as three different flip angles. One is 45, other is 90, the other is 135 degrees. So let's ask for Ch. What are you going to get for each of the case? Sine of alpha is going to be 1 by root 2. So when alpha is 90 degrees, sine 90 is going to be 1. If you have sine of 135, sine of 135 is nothing but sine of 90 plus 45, sine 90 cos 45 plus cos 90 sine 45. Cos 90 is 0, so you're going to get 1 over square root of 2. Let's take a look at the same thing for Ch2 spin system. When you have sine of alpha cos of alpha, you're going to get 1 over 2 here. On the other hand, when you set it to 90 degrees, cos of alpha will go to 0, so Ch2 is not going to be present in the DEPT experiment with 90 degree flip angle. Now the same case for 135, that's going to be sine 135, which we just realized is sine 45 times cos 135, cos 90 plus 45. You would realize that this is nothing but minus sine of 45. So you're going to end up with a minus 1 over 2. Now let's just go to Ch3. Ch3, you have cos square of alpha times sine of alpha. So it's going to be 1 over 2 root 2. 90 degrees will take it to 0. 135 will just going to be square of sine 45. That's going to be 1 over 2 root 2 again. And therefore, what you are able to realize is that when you set the flip angle as 45 degrees, you get all the three CH, CH2 and CH3 being positive. When you set the experiment to 90 degrees, you only get CH spins. But on the other hand, when you set the experiment to 135, you end up getting CH and CH3 being positive while CH2 being negative. So I hope this helps you understand how CH2s can be easily distinguished from CH and CH3. And all that one has to do is to repeat the experiment at 90 and 135. 90 is only going to give CH, while difference between 90 and 135 will give you what is CH versus CH3, and CH2 will be opposite of phase. There's one important point that I did not write throughout this, is that I'm sure you remember the initial density matrix is weighted with omega h. So therefore, you get a sensitivity boost that accompanies, therefore, this polarization transfer finally ends up providing a higher sensitivity than a carbon direct detect experiment, and at the same time helps you obtain a spectral editing based on CH, CH2 and CH3